Hello students, today I am going to explain a eye pattern or a eye diagram. So here in a band limited channel, the pulse appearing at the output of the system will be dispersed over an interval which is longer than that of the transmitted pulse. Eye diagram is a very effective tool for digital signal analysis during real-time experiments. An eye pattern is a practical technique for determining the severity of the degradations introduced by ISI and channel noise into the line-coded digital pulses in baseband transmission. That is, eye pattern is a simple and convenient engineering tool applied on received signals for studying the effects of ISI, accuracy of a timing extraction, noise immunity, determining the bit error rate. And also, the eye diagram provides information about the state of the channel and the quality of the received pulse. And also, this information it is useful for faithful detection of a received signal and determination of overall performance of the digital communication system. The eye pattern. So how to generate an eye pattern or an eye diagram? First, the received pulse dispersed in time due to channel noise and ISI is given to the vertical input of the oscilloscope. And a sawtooth type base generator is provided to its horizontal input at the transmitted bit rate R equals 1 by T. And the waveforms is successive symbol intervals are translated into one interval on the oscilloscope display for the case of a binary wave for which t is equal to tb. The symbol clock is applied to the external trigger input. The resulting display is called an eye pattern because of its resemblance to the human eye for binary waves. The interior region of the eye pattern is called the eye opening. When the received bit pattern is ideal, the oscilloscope display will show two vertical lines across its display. If the bit sequence is slightly distorted, the oscilloscope display shows the pattern which is very similar to the human eye. The central position of the pattern representing the opening of the eye. If the received digital is further distorted, the human eye appears to have closed. So this is the first we have taken a binary data, and next one is an eye pattern here, where the binary data, the positive terminal we have fixed here and the negative terminal here we have fixed here. Next, the width of the eye opening defines the time interval over which the received wave can be sampled without error from ISI. It is apparent that the preferred time for sampling is the instant of time at which the eye is open widest, and the sensitivity of the system to timing error is determined by the rate of closure of the eye as the sampling time is varied, and the height of the eye opening at a specified sampling time defines the margin over noise. Now this is an eye pattern here. So when the effect of intersymbol interference is severe, the traces from the upper portion of the eye pattern crosses the traces from the lower portion, with the result that the eye is completely closed. In such a situation, it is impossible to avoid errors due to combined presence of intersymbol interference and noise in the system, and a solution has to be found to correct for them. So this is an interpretation of an eye pattern diagram. So here eye pattern, waveform and eye diagram, it has written it here. Ideal channel, infinite bandwidth, pulse received without distortion. Next we are considering the distortion channel, finite bandwidth, received signal will rounded and spread out. Next noise channel, ISI is not zero, the eye closed partially at the midpoint. So here the width of the eye opening defines the time interval over which the received signal can be sampled without error from ISI, and also the sensitivity of the system to timing errors is determined by the rate of closure of the eye as the sampling time is varied. The height of the eye opening at a specified sampling time defines the noise margin of the system. So this is a interpretation of an eye diagram here. This is a noise margin, the sensitivity of the timing error, distortion of zero crossing, timing error. So here also it is the figure shows here signal expression or wasted power and best time to sample, opening of the eye, close of the eye, everything it has mentioned in this interpretation of the eye diagram. So this is also an eye diagram. So baseband M array scheme. So next we have baseband binary data transmission system, where we are considering here the same transmitter, channel as well as a receiver. In the above figure, the output of the pulse generator consists of binary pulses. That is a pulses with one of two possible amplitude levels. On the other hand, in a baseband M array PAM system, the output of the pulse generator takes on one of the M possible amplitude levels with the M an integer power of 2. This is a M array coding. It is often advantageous to encode at a level higher than binary, where there are more than two conditions possible. The number of bits necessary to produce a given number of conditions is expressed mathematically as n is equal to log m base 2, where n is equal to number of bits necessary and m is equal to number of conditions or level or combinations with n bits. Next, we have baseband M array PAM. So here it produces one of a m possible amplitude level, and t is equal to symbol duration. 1 by t is the signaling rate, and tb is equal to bit duration, where t is equal to tb log m base 2. And to realize the same, average probability of the symbol error transmitted power must be increased by a factor of m log base 2 m compared to binary PAM. So next we have baseband M array schemes. So here binary modulation transmit 1 bit per signal interval with the bandwidth efficiency of 1 bps per hertz, and also M array modulation more than 1 bit be transmitted per signaling interval, and also it allows a greater bit rates for the same bandwidth, and also it transmits m is equal to 2 power n symbols of each signaling interval. And also m array modulation can be done by using multiple discrete amplitude levels or multiple phase states, or with a combination of these. Next, we have baseband M array schemes. An M array PAM system with a signal alphabet that contain M equally likely and statistically independent symbols, with the symbol duration denoted by two symbols. And also M array PAM system is able to transmit information at a rate that is m log m base 2 faster than the corresponding binary PAM system for a fixed channel bandwidth. And also M array is well suited for the transmission of digital data over channels that offer a limited bandwidth and a high signal to noise ratio. Equalization. In telecommunication, equalization is the reversal of distortion in, incurred by a signal transmitted through a channel. And also equalizers are used to render the frequency response for instance of a telephone line flat from end to end. And also an adaptive equalizer is an equalizer that automatically adapts to time varying properties of the communication channel. Next, we have equalization. An equalizer is a specially designed filter which is located between the demodulator and the decision making device at the receiver. And also, the equalizer should be able to adapt to the changes in channel characteristics with the time. And also, in order to eliminate the effects of amplitude, frequency, and phase distortion causing ISI, amplitude delay and phase equalizers are used respectively. So this is a general block diagram of equalization, where input we have taken channel HC of f equals HEQ of f, and at the output we are getting the channel output here. Next, here there are two modes of operating the adaptive equalizer. So that is during the training period, a known sequence is transmitted and a synchronized version of this signal is generated in the receiver, where it is applied to the adaptive equalizer as the desired response. The training sequence may consist of a PN sequence. When the training period is completed, the adaptive equalizer switches to its second mode of operation, the decision directed mode. In this mode of operation, the error signal equals E of NT is equal to B of NT minus Y of NT. So next, here this is the adaptive equalizer need to train by a known fixed length of training sequence bits for a minimum bit error rate. This is equalization. So here adaptive, we have taken the block diagram, that is modes of operation of an adaptive equalizer. So method of implementing adaptive equalizers are analog charge coupled devices technology, hardwired digital implementation, programmable digital using microprocessors. So this is an linear adaptive taped delayed liner equalizer. Next, here we have equalizers, that is adaptive equalizer, channel equalizer have played an important role in digital communication system. And also this equalizer works like an inverse filter which is placed at the front end of the receiver. Its transfer function is inverse to the transfer function of the associate channel, and also it is able to reduce the error causes between the desired and estimated signal. And also this is achieved through a process of training. During this period of transmitter transmits a fixed data sequence and the receiver has a copy of the same.